This video is on centripetal and centrifugal forces. And interestingly enough, I'm going to open up this video by saying that they don't really exist. Interestingly enough, centripetal and centrifugal forces are truthfully nothing different than gravity or normal or friction. It's more like centripetal and centrifugal are directions, similar to how in classic mechanics we talk about x direction forces, y direction forces, and the vectors and breaking them up. It's the same deal. To give you an example, let's take something like your car is making a turn on the road. So people would argue that there's a centripetal force that's pulling the car inwards on the circle. But the truth is, there isn't. The car is indeed making a turn, and there is a collection of forces or a singular force that is pushing it towards the middle of the circle, but that force is actually just friction. So instead of thinking of centripetal and centrifugal as a new unique force, think of it instead as a new direction. So think of a circle that has a force acting inwards. Any forces acting inwards we would call positive, and any circle that has forces acting outwards, that would be negative. So thinking back to our car making a right turn, since the circle is here and the friction is acting inwards, this would be a positive force of friction. Other examples would be in, say, the normal force. Let me zoom out and make this a little bigger. Normal force would be experienced on something, say, a hilly road. Perhaps as the car comes over the top of a hill, you would witness this experience, these forces. If you've ever gone over a hill and you hit the gas, which for all intents and purposes I don't recommend you do, but if you did, there's a chance you might actually become airborne in this situation and lift off the ground. When you're rounding the top of the hill, we can model the top of the hill like a circle, and you would have the force of gravity acting inwards on the circle. So even though it's pointing down, that would be a positive force, and you would have the normal force acting upwards. If you're curious how to solve a problem like this, how would I know how much speed I need while rounding the top of this hill in order to go airborne? You essentially need to make the normal force zero, because if the normal force is zero, your tires are no longer in contact with the road. Continuing onwards with the car and the hill example, when we get into this dip in the hill here, we have another circle. And this time, gravity's still pointing downwards, but it's actually going to be a negative force. It'd be a negative force because it's pointing outwards from the circle. And then you would have an upwards normal force. If you've ever gone on a roller coaster, and perhaps part of the roller coaster ride involves some hills up and down, up and down, up and down. When you're at the top of the hills, here, here, and here, as the roller coaster, now the first hill kind of pulls you up and then it drops you, and then you go up, down, up, down, up, down. On these ups, you might feel the sensation like you're about to be thrown out of your seat. That's the same thing that's happening here with the car coming over the top of the hill. And then when you're at the dips, such as here and here, you feel like you're being slammed down into the seat, and that's the same effect as here. The other thing I want to hit on is another classic place that the centripetal or centrifugal force manifests itself in is something like a witch's wheel, if we want to stick with the amusement park theme. A witch's wheel is the big drum, and the riders are inside the drum, and at first they're standing with their back against the wall. The drum is going to begin to spin faster and faster and faster. And what's going to happen is we have gravity down per usual, but the passenger is going to feel the sensation as though they're being slammed against the wall, generating a normal force. This is our centripetal force. It's not Fc for centripetal, it's Fn for normal. It's a normal force because your back is a solid surface and the wall is a solid surface. And then the normal force creates friction. And the force of friction, again, has to be 90 degrees to the normal force. The force of friction is what's countering the force of gravity. On some of these rides, what they'll do is the floor underneath the rider will drop out and their feet will essentially be dangling. It seems a little bit scary, but as long as the ride spins fast enough, generating a big enough normal force, you will generate a strong enough force of friction to counter gravity and prevent the rider from falling. Dangerous? Debatable. So, once again, just to remind you, any inward forces of the circle would be considered positive. So, this is the plane of the circle. I'm trying to represent three dimensions here in a two-dimensional uh, screen. This normal force is pointing inwards, so we would call it positive. Other places you can kind of see the witch's wheel would be like a washer or a dryer. The washing machine typically has a center piece here with some fins on it to help spin the clothes around, and then it's a big drum. And on the side of the drum, you have holes. And the purpose of this is the last cycle in the wash is to take all of your clothes and spin them really, really fast. So your clothes end up getting smashed against the side of the walls. The water, however, will seep through these holes and thus help start to dry your clothes. If you took your clothes completely soaking wet, dunked in a giant tub of water, and then threw them right in the dryer, your dryer's going to have an extremely difficult time getting rid of that much water off the clothes. So we do a rapid spin cycle towards the end to help dry out your clothes. Sorry about the quality of that drawing. It's meh at best. Now, once we do figure out what the centripetal force is, whether it happens to be a normal force, such as the witch's wheel or the dryer or washing machine, or friction, like on, say, the tires of a vehicle, or even gravity, which could be used to simulate gravity in a space station. The point is, when you sum up these forces in the centripetal or centrifugal world, they, like all summation of forces, do equal ma. But this time, a is v squared over r. And that's going to happen in all of these circular type motion problems.